And welcome back for our final keynote of the day, going along the future of low frequency communications. We still have the best question award, so I would recommend you to participate. Any questions and comments are more than welcome. Isma, you already started with the question, what band are you aiming for? I've been told that will be answered in the presentation relatively early on. Um, our speaker has developed technology around low frequencies for more than a decade, motivated by first responder and military uses for getting frequencies into buildings. You can imagine what technology like this can do, for example, after an earthquake. We have Brian M. Sadler.
Number of radios actually packed into your cell phone and talking to towers and wired things. And generally speaking, all of this from a wireless perspective is about one hop into the wired infrastructure. It's really the massive wired infrastructure of cell towers sprouting up all over the world, which makes all of this possible. And now the thrust is to higher frequencies. We want more bandwidth. How do we get more bandwidth? We go to higher frequency. And so we're seeing that now in explosion of research in millimeter waves, intelligent surfaces, and autonomous vehicles potentially exploiting mobility now. So bringing that into the picture for the future of 5G, 6G. So this convergence of technologies is pretty interesting. And as we go up in frequency, we're really driven by this need for line of sight. As we go up in frequency, these signals do not penetrate. But there's a sort of untapped potential, and this is the subject of my talk. When you look at very low frequencies where the wavelengths are quite long, like what's called high frequency, HF, these frequencies, as we go down there, the wavelengths are so long, they actually can bounce off of particles in the ionosphere, and you can get multipath bounce like that and go all the way around the Earth. And this is long known, long studied, and difficult to manage because you're relying on the ionospheric conditions. But here's the subject of my talk. There's an opportunity in this sort of upper HF, lower VHF, and I'm going to roughly call that 25 to 100 megahertz, where the wavelengths are meters long. And this brings very special opportunities, but also confounding in terms of technology, which has limited the general application and interest in this space for a while. With the future of networking, I think we're going to embrace things that are ad hoc and dynamic, especially autonomous vehicles. And if you think about the autonomous vehicle problem, how much do you want to rely on infrastructure? Do you want to assume it's there or not? And generally, as vehicles become more and more autonomous, less reliant on human interaction, the number of interactions goes down per unit time. We need something which is sort of persistent low bandwidth connectivity for control, for synchronization, for coordination. So it's not the high bandwidth continuous interaction that we're talking about. The other thing that confounds us in this space is the ability to have those signals penetrate through buildings. The microwave is kind of a nice compromise in the sense that it does penetrate. It will also go through apertures like windows and bounce around. But you're all familiar over the years with the challenges of getting cell phone connectivity when you're deep inside a building or if there's a lot of metal and so on. And another problem that I've been interested in, of course, working for the Army for a long time, is this question of disaster response, first responder. What do you do when your infrastructure has failed? How do you track topology of multiple agents? Could be humans and autonomous agents. And how does a human interact with a swarm of such agents? So whether it's a disaster response or going into Fukushima, these are major challenges, and we generally still lack good solutions. So let's talk about some of the basic advantages of using low frequency. The first is that from basic electromagnetics, as the wavelength gets long, the interaction of the electromagnetic wave with a potential scatterer depends on the size of the scatterer versus the size of the wavelength. So when you're in microwave, literally say centimeter kind of wavelength, it interacts richly with the environment. There are many, many objects and things which look like scatterers. As the wavelength becomes meters long, that becomes less and less true. And this is, in a nutshell, perhaps the key advantage for going to low frequency. It turns out the channels are rather benign, and you can do things like simple multi-user coding and manage interference in ways that are very challenging in microwave. As these wavelengths get long, in meters, then classically antennas would also be expected to get large. The size of the aperture really matters. The classic sort of dipole is lambda over 2, wavelength over 2. So if you're at a 7.5 meter, then you need a 3 meter, dipole is 3 meters. However, we now understand sub-wavelength antenna theory very well, and we're good at making such antennas and understanding the exact trade-offs. And in addition, these low frequencies, the propagation can be such that you can actually do beamforming, not in the sense of MIMO based on scattering, but more like classic free space beamforming. And it's possible to do this in a distributed way, meaning that, for example, you have multiple robots that are not wired together, but they collaborate in order to communicate by doing beamforming together, called distributed beamforming. And the story here is really about low power and short range. The effective use of low power and short range, I think, is going to be a substantial contribution in future wireless. And this makes things easier to manage. The propagation can be quite clean, and I'll show you examples. So the bottom line here is that this unique penetration and propagation enables connectivity, directionality, even through buildings, and persistent connectivity. And that, I think, will be an important technical contribution for ad hoc and dynamic networking. And I believe that that is the future of networking eventually. So let's look at from a phase perspective. So one of the issues you run into when you start to do this kind of networking is that the standard statistical models don't hold anymore. This is not multipath. We can't rely on Rayleigh-Ricean kinds of statistical models based on multipath. Actually, what you'd like to do is evaluate Maxwell's equations. And as scary as that sounds, it is quite possible. And here are some simulations. The point of this slide is that this is a rendered scene roughly taken from this chunk of downtown LA. And what you're seeing here is electromagnetic code. So this is evaluating Maxwell's equations from a single antenna, just showing you the phase. This doesn't represent signal loss. And you can see the phase front at 40 megahertz. Eventually it starts to ripple due to diffraction, refraction. This is completely different than essentially random kind of phase you see at the higher frequencies because of the rich multipath. This is just another example, pretty simple scene with, realistic dielectric material properties, comparing 20 megahertz and 100. You don't have to go too many wavelengths, even at 100, before you start to see this sort of phase distortion, which is caused by reflection, which is not present in the lower frequency. So another really interesting thing that happens is the penetration. So we've done a lot of really sort of detailed, highly calibrated comparisons. This is an example of comparing 40 and 2.4 gig in these kind of scenes that you see here. I want to emphasize that the power comparison here is rigorously fair and quite calibrated. What you see circled there is the path loss difference comparing 2.4, sort of typical microwave, against 40. So the 40 megahertz, because of this penetration, is giving a significant power advantage. We've done more studies like this kind of scene. This is actually a military testing center. We go there, we roll robots around. Notice the low transmit power here. We did a number of tests. I challenged our guys. I said, okay, let's say we use simple narrowband pulses or single tone transmissions. Are we detecting multipath in this environment? So we set up a statistical test to see if we were seeing multipath. And the answer was generally no. From a statistical perspective, in this environment, at these low powers, it ranges out to a couple hundred meters, penetrating through many buildings. We didn't see any multipath. That's not always true, but interesting. So the channel is pretty benign, especially at short range, low power, and especially when we're low Earth, low to the Earth. So we can do things like classic multi-user code division multiple access. And this is an example here. These codes in particular are interesting because they have what's called a zero cross-correlation zone. Now this means that the codes are designed so that they can be slightly shifted with respect to each other and still be orthogonal. And these kind of designs are interesting. So they're robust to some timing synchronization error. They're also pretty robust to frequency offsets, small frequency offsets. So keeping in mind that we are at relatively low frequency with relatively small bandwidth, then the timing constraint here is not very difficult to achieve at all, actually, in a distributed way. And you can see here in this simulation, 16 interferers, and still we're getting good orthogonality. We've carried out experiments. This is an example. This gray area here is a building. The white area is courtyards. We set up a transmit system based on software-defined radio. They're cabled together. And then we introduce offsets in timing and frequency so that we can control and measure how much offset we can tolerate. And we get results like this. You see two users here, the signal-to-noise ratio of one versus the other against relative offset, the delay. This is using these zero correlation zone codes. And eventually, the channel breaks down. You see delay 5, delay 9. We start to lose orthogonality. I want to emphasize that the receiver here is just a single user correlator. There is literally no multi-user detector going on here at all. There's another interesting piece to the technology, and I'm only going to show you one slide on this, and I'll refer to this survey article you see cited down there. There's actually quite a bit of science, but the basic message is the following. The red curve here is what's called the Chu-Wheeler limit. This curve defines for us fundamental limits on passive antennas. So you can think of the x-axis, this Ka axis, as essentially a measure of size. It's actually in terms of a sphere encasing the antenna. And so as we go smaller and smaller, the antenna aperture is getting smaller and smaller. Okay. So at 0.8, we're below we're sub-wavelength, all of these. By the time we get to the left side of the curve, these antennas are quite small with respect to the wavelength, like 1/100th of the wavelength and so on. The y-axis is a measure of the efficiency. It's fractional bandwidth and radiation efficiency. So it's telling you about the achievable bandwidth and the efficiency you can achieve. And a passive antenna cannot go above this curve. What you see here is all these different designs. So many antenna designers have landed near this space looking at different sizes, and you see some examples here. Another interesting thing about the low frequency is that you can couple the antenna with the platform, so they can be co-designed and you can take advantage of that. I don't want to trivialize this question, because as these wavelengths get long, the antenna tends to see nearby objects, especially those within, say, lambda/2, lambda/4, as part of the antenna. They will couple electromagnetically. And this is a very interesting phenomenon. There is a lot of science there. In fact, we have work on how you can exploit that. So I don't have time to go too far into that, but I want you to know that the science of this is pretty well understood now, and actually we can take advantage of this coupling in the environment in interesting ways. So I talked a little bit about robots, and one of the motivations for this work for me initially was this question of multi-robot networking. So we want to have teams of autonomous agents, and we want them to operate in complex, difficult environments. We want them to go in and out of buildings, and we want them to be potentially fairly far away from a human user that they're interacting with. And then the question is, well, how do I do the comms? Because, well, you know, it's back to this penetration and ranging kind of question. And I can lay down breadcrumbs, I can use repeaters, I can do a lot of that sort of thing. I can use robots to act as repeaters. So I can set up mobile topologies to support networking, and I can do this at various frequencies. And all those tools are good, and I've worked on all those tools myself. But the low frequency opportunity is kind of an interesting one, and I want to show you how we can do distributed beamforming using multiple platforms that I mentioned earlier. So here's a electromagnetic simulation of this building scene that I showed you before. On the left-hand side, what you're seeing is an 8-element linear array steering energy. This is just doing classic narrow band beam steering. On the left is just the ground, and on the right is with the buildings present. So what's interesting is that we get directionality. Now, this is a measure of power, but you see directionality in the power despite the presence of the buildings because of this penetration. So this opens up a bunch of interesting questions, and I'll try and summarize that in this one chart here. When you're working with these robots, one of the questions, an immediate question is, how are they relatively positioned? Do we know their positions relative to each other? So if you build an array and wire it together, you have precise information about the location of the antennas. You have precise time synchronization and frequency synchronization. When you go to the distributed regime, that may or may not be true. So this fan here sort of describes positioning error. All the way over on the left would be I have perfect positioning, and then I can use a predictive beam shape, design how I want to steer the beam. On the far right then is complete unknown positioning. I don't know how to set the phasing. And I have techniques for that too, but that would rely on feedback from a user. So I can transmit and then improve the beam adaptively. So it turns out that in this small localization error, say on the order of even a meter localization error, that's sufficient to get a good beamform solution. So one of the things in this work that I'm citing here is this sort of notion of small error regime, and we define that rigorously. And you can see this definition by this blue curve here, which even as you go up to 200 megahertz, the localization error accuracy starts to get pretty small. Well, you know, when you go up to microwave, I mean, you need localization accuracy that is sub-wavelength. And as the wavelengths get high, then the localization really gets challenging. But down at, say, 40 megahertz, about a meter square of error tolerance is okay, and I can still get a pretty decent beamforming solution because the wavelength is long. And with robots today, we can do much better than a square meter of error tolerance. Why do we want to do this? Of course, we get this n-squared processing gain. And this is sort of free space, right? If I have 2 agents, I get 6 decibels. By the time I get to 8 agents, 18 decibels. So you get a lot of gain as you add a few, as you start with just a few agents. And we realize this gain, actually, even when we're in these complex environments. We also solve the timing synchronization problem. This is an example of how we can do that, where we use a separate local communication amongst the agents to do this. This is illustrating a particular way, sort of a leader-follower approach. Essentially, one of the agents, where everyone is synchronizing to one of the agent's clocks. So we wouldn't want to necessarily assume that we have GPS or some other broadcast clock. If we do have a broadcast clock in the environment, then that's perfectly good and we can take advantage of it. Here's an experiment with 2 agents, and I'll just to show you that we can do this experimentally. If you look at the lower left, you see the 2 agents down there, agent 1, agent 2, and then the client is the receiver, and client path 1 and 2. So like client path 1, this robot rolls away in a straight line away from them, and in client path 2, it goes around this sort of arc, and we make measurements. And you look in the upper right, you see that we're realizing the beamforming gain. And we're doing this autonomously. These 2 agents are setting up this wireless timing synchronization, and this is without feedback. So we can do this with feedback. It depends on the setting. But the notion here is that you have multiple agents that form a beam and transmit to the client feedback some information, and you iteratively improve. You can also add in jamming or null forming. And this notion of null forming is that I transmit energy and form a null towards the client so that I'm transmitting noise elsewhere. And I may or may not have accurate understanding or control of that, but you can play in this space of transmitting energy away from the client and transmitting the message to the client, and you can do this with relatively simple algorithms. This is a simulation in an urban setting of doing this. This is pulled out of the electromagnetic kind of simulations that I showed you before. And it seems to work pretty well, at least as far as what we'll predict in a complex environment. So I think that the technology is coming along to do low frequency and to revisit these frequencies and how we use them. And so my prediction for the future is that they're going to be integrated into what we do now in multi-radio networks. So it's important to keep in mind, this is not a replacement, right? This is not a solution. It is part of a solution. It's a new tool, but it is really about low power, short range, and combining these cognitive techniques. But I really see the future in the ad hoc and dynamics as we add in autonomy, as we add in a lot of these other things that we want to do that are going to become much more, intelligent. But I believe the baseline technology is already present, and I think that eventually we will revisit the use of these low frequencies and bring this interesting combination of technologies to bear to do that. So that concludes my talk, and be happy to discuss.
Thank you so much, Brian M. Sadler. What would you like to know about low-frequency communications? Type your questions in the chat, and we'll discuss, of course, the answers. And while people are doing that, I'm wondering, you mentioned that this is based on old, well-known technology, even though it's a new tool. Why is it not used more already?
It's an interesting question because it's true for a number of reasons. Like there were some pieces that had to come along, like the antennas. And it also means that we're going to rethink how we use this kind of spectrum. And so there's regulatory questions and things like that. Traditionally, the low frequencies have been used for long-range broadcast, like towers, blasting to police cars, that kind of thing. And what I'm talking about is bringing a lot more cognition to this, bringing the multi-user thinking, bringing power control, coding, and all those things. So it really requires a combination of cognitive pieces to come to bear. And so it's not extremely simple, but I think, another part of the answer to your question is that the need hasn't been there. We haven't really said, well, gee, I really need to take my 10 autonomous robots and have them be able to go into this burning building. But all of that technology is coming, right? All the autonomy, the human interaction, right? Because of the advances in AI, ML, and the perception pieces and things now, and UAVs. And so the autonomy technology has really exploded. And we're going to struggle with the networking to keep up. So one of the things I advocate is a sort of co-design of autonomous systems and the networking piece, and not try and glue them together after the fact.
Okay, that makes sense. We have a couple of questions. The first one from Andui Pam. What's the greatest challenge when going from the simulation to the realization of the approach in reality?
It's a great question because, this is another reason why this area doesn't progress rapidly. It's because we don't have real simple models for the propagation. It's very environmentally dependent. Right, so those are all important issues. But for our experiments, it wasn't that hard to get into it from a software-defined radio perspective, using small antennas. But like any wireless problem, you have a sort of immediate disconnect between your simulation, which might give you something which is on average or very specific to a specific environment, versus what you're really going to see when you get there. But this means you need the we need the cognition and the adaptation. We need to think that way.
Okay. Tanya asks how the security of information will be guaranteed due to the lack of resources and limited battery power.
Say that again.
So she wonders how the security of information will be guaranteed due to the lack of resources and limited battery power.
Yeah, security of information. So the question is really, the security is a kind of multi-layer question, right? I mean, it's everything from cyber to encryption, all these things. But I think the question about battery power is such that if I have a small, cheap device which has relatively low capability, how do I ensure that right? I can't load it up with expensive, computationally complex, secure things. So your question is actually much broader than, right? The question's a lot broader than just low frequency. Now, I think in the multi-radio context, right, where we are now in cellular and where we're going, 5G, 6G, and bringing in UAVs and things, my view of the security is that it's a multi-layered cake. From physical layer security to encryption to all these things, verification. But there's an interesting new level of security needed when I start to say, okay, I'm going to task these 10 robots to go into that burning building and see if there's anybody in there that needs rescued, right? And
they'll probably left alone. If you do that somewhere else, small kids might take them or something else. It's really a physical problem then, I suppose.
There's just all kinds of new issues there. So, but I believe that if you accept that as we get into 5G, 6G, we're going to make these things more and more secure and have more and more tools and more capabilities, adding the low frequency in will enhance that. It'll give you new ways actually to maintain connectivity when you might otherwise lose it, especially if your infrastructure fails. So I think actually it adds more things into your kit.
Okay. Reginald wonders, the simulation and tests shown were on land. Would it work underwater?
Yeah, so there's a lot of historical work in low frequency for broadcast generally. And there was a lot of work for propagation over the ocean, for example. And it varies quite a lot depending on wavelengths. You can get ducting over the ocean. I mean, there are studies that show, for example, in the low part of the VHF where a watt of transmit power could go miles and miles because of favorable conditions. So it has been studied, and it has been, this kind of thing has been utilized in the maritime kind of regime. What's interesting is that it's even there, it's very environmentally dependent, and you have to be adaptive in terms of power levels, rate adaptation, frequency allocations. So I think, I'm not trying to mention it, but dynamic spectrum access is also an important piece of the puzzle here.
Now you mentioned over water, and how about underwater? Has that been studied as well?
The underwater and generally getting into water and getting into the earth is very challenging. And, RF radio frequency, it hits the water and it just says, right, you just don't get the kind of right? So like underwater, you go to acoustics for this very reason, right? Acoustically, you can go down to extremely low frequencies. Like you can go acoustically many, many meters of wavelength, and that'll propagate, right? So, you can hear whales 1,000 miles away because of this, but it's acoustic, not radio.
Makes sense.
The ground penetration is also another interesting question. And as the wavelength gets longer and longer and longer, it will tend to penetrate into the earth, but that's a bit different story than trying to penetrate through a building.
Okay, thank you so much. So I'm going to ask you for the best question. We had 3 from our participants. We had Andui, who asked about simulation to reality, Tanya, who asked about security, and Reginald, who asked about it working underwater. Which of these was the best question for you?
The second and third questions were good, quite general, and I gave pretty general answers where I deviated away from what I was talking about. But I think the first question
before we go on, I see we have a new question in. So I am going to interrupt you and ask the final one. Actually, we have a few coming in now. Fatime asked, do you think the collected data could be available as open data to promote innovation in this area?
I do think there's a need for data sets. I'm trying to think if I've published data. I'd have to take that under advisement. Part of the issue is where I work, and but I agree. I agree that data sets would be highly useful in this space.
Okay, and another question by Ifeo Lua. How is the phase noise cancellation algorithm developed to improve reliability in low-frequency communication compared to other emerging technologies for improving the reliability of low-frequency communication systems, such as cognitive radio or software-defined radio?
Yeah, so it's my belief that the solutions that would emerge eventually will be highly cognitive, highly software-driven, and that's going to span, I think, coding, power control, frequency dynamics, dynamic spectrum. So I think all these tools are really important here because of the variation that you see in the environment and the propagation. And because, like I mentioned, over water, you could have a watt that goes a long way. So you can actually propagate a long way. Mm-hmm. And that might be very undesirable. So power control becomes a really critical aspect. And it's a funny question, again, and this is a challenge for future regulators, because you can't just say, well, you can only go up to a half watt. A half watt might be blastingly loud in one environment, and you have to really throttle that back. So one of the challenges is, as you add all these dynamics in, how do you regulate the thing? What's the policy, right? This is what happened in dynamic spectrum access when it first appeared. It's probably still true. How do you regulate this? What's the policy? How do I know if your device is obeying that policy? These are all challenges, right? We face the same challenges in autonomy. Here's an autonomous vehicle. How do you test it and know that it's reliable and it's right? The Google solution is drive another 1,000,000 miles. But, so the short answer to your question is yes, for all of that. We need software-driven solutions to take advantage of the tools that we have.
What I'm hearing is that the environment is the biggest challenge for all of this. Is that correct?
Yeah, you need to adapt to the environment, even more so than you would in cellular, for example. And when you get away from infrastructure, right? If I put up cell towers and then I walk around and I go, there's a dead spot over here, and we put up a little micro tower. Well, that's great if you're building this out and you happen to live in Manhattan. That's fantastic. If you live in North Dakota, right? And so,
there's a difference.
But I'm also talking about environments where you lost your infrastructure, okay? Your tower just fell over. It got hit by whatever it is. There are plenty of places in the world where we can anticipate climate disasters, all kinds of health disasters. We need the capabilities to be able to send autonomy into these areas and for them to immediately network and to link with the infrastructure if it's there, but not be wholly reliant on it. I think there's a very rich interplay in the future that's going to happen. And I think that, that this is one of the reasons why I confidently 0.9 predict that this is going to happen.
Okay. I think that's a great closer for now. So now we've had 5 questions. So I'm going to ask you once again the best question, just to reiterate. We had Andoi asking about the simulation to reality. We have Tanya asking about security. Reginald asking about the possibility for underwater. We have Fatima who asked about the possibility to open data. And we had Ifeolua who asked about the phase noise cancellation and the other possibilities. What would be your favorite question?
So I liked all the questions. And the last one is interesting, but I'll come back to the first one because of this, sim to real gap. This is the term that we use in autonomy, sim to real. I simulate this robot doing all these things and I put it in the real environment and it just, it doesn't work at all, or it's caught, right? So this is a challenge in this area because getting the models right is really hard. And how do we model penetration? Well, you know what? We calculate Maxwell's equations, okay? We have code that runs on high performance computing clusters in order to do large scenes. This is a real challenge. So this whole question of channel modeling and this mix of what we simulate and how we adapt, really gets to the crux of it. So I'll pick that one. I hope you get a good prize.
Yes, he does. He will get a pass to one of our upcoming conferences this year. So congratulations, Andui. Okay, Brian, thank you so much for your talk, and hopefully we'll see you again.
Thanks a lot.